So buffer solution is a solution which can resist the change in pH even by adding a small quantity of an acid or with a small quantity of base. So what is the formula we have? pH which is equal to negative logarithm of base 10 to the molar concentration of H plus ion. Molar concentration of the H plus ion is a square root of Ka into C. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called equilibrium. Under this unit, we have learned that how to derive an expression for pH plus POH which is equal to 14, and also we have learned one more derivation, that is pKa plus pKb which is equal to 14, which is nothing but a ionic product of water. In addition to that, we also learned about the ionization constant for the weak electrolyte, and we have understood that what are the salts, and also we have solved the sum of the numerical. Today, let us move on to the next topic of this unit by understanding what is a buffer solution and what are the types of buffer solutions will be there, and how to solve the sum of the numerical based upon the pH as well as with the POH we are going to understand in this session. So first of all, we will see what is a buffer solution. Buffer solution is a solution which can resist the change in the pH even though when a small quantity of acid or base which has been added to the same solution. Such solutions are said to be buffer. Okay, and I can take the example to explain for this. Here I have taken a weak electrolyte, that is acetic acid. We know that acetic acid which dissociated to give acetate ion as well as with a H plus ion. Now for this weak electrolyte, okay, this is my weak electrolyte. Okay, to this weak electrolyte I am going to add a small quantity of strong alkali. So what will happen if I add a small quantity of a strong alkali? The OH minus ion from the alkali combines with the H plus ions of the weak electrolyte and forms a water molecule. As a result of this, the pH of this acetic acid does not get alter even though when you added a small quantity of base. Such solutions are said to be buffer solution. So what is a buffer solution? It is a solution which do not change or it will resist the change in pH even though when you add a small quantity of acids or bases. Similarly, I can take one more example. This is a strong base, correct? No, this is a strong base and the name of this compound is sodium acetate. We know that the sodium acetate which dissociated to give acetate ion as well as with a sodium ion. To this solution, if I add small amount of acid, we know that any acid can dissociate to give H plus ion, correct? No? So this H plus ion combines with the acetate ion and forms a acetic acid. Thereby, the pH of the solutions does not get altered. Such solutions are said to be buffer solution. Okay, and it is very important for the examination point of view and it can be asked for 1 mark. So they can ask you what is a buffer solution, given example. So buffer solution is a solution which can resist the change in pH even by adding a small quantity of an acid or with a small quantity of base. Now let us understand what are the types of buffer solutions will be there. Generally, there are 3 types of buffer solution will be there. One is acidic buffer, basic buffer, and the last one is neutral buffer. So acidic buffer, basic buffer and the neutral buffer. We'll understand one by 1. First, I'll go with the acidic buffer. And acidic buffer is a mixture of weak acid and its salts of strong base. So, here I have taken out the weak acid and its salts of strong base is sodium acetate. Such solutions are forming a buffer solution. So, in the acidic buffer, we are taking the weak acid with the salts of strong base. So, when it is formed, such solutions are said to be acidic buffer. Similarly, we have one more buffer, that is basic buffer. These are the buffer solution which are formed by the mixture of weak base to its salts of strong acids. Here the weak base is ammonium hydroxide and with the strong acid, that is ammonium chloride. When we mix these two, we will get the buffer solution and it is basic in nature. Similarly, we have one more buffer that is called as neutral buffer and it is a mixture of weak acid with a weak base. Okay, such mixtures are known as what? Neutral buffer, and it is an example is ammonium acetate. Ammonium acetate is a mixture of weak acid with a weak base. So, you can take CH3, COOH and NH4OH. Okay, this is a weak acid and this is a weak base. So, when we mix, when we mix these two components, we will get ammonium acetate with a formation of water molecule. So, this is an example for neutral buffer. So, this is how we can understand the types of buffer solution. Now, let us solve some of the numerical based upon the pH and pOH, because in our last session, we have solved only the few problems based upon the pH. Today, we will continue with the remaining numericals of the pH as well as with the pOH. Okay. The first problem will be goes like this. The concentration of hydrogen ion in the sample of soft drink is 3.8 into 10 to the power of minus 3 molar. What is its pH? So, what is the formula we have? pH which is equal to negative logarithm of base 10 to the molar concentration of H plus ion. So, they have given the H plus ion concentration. So, negative log, I will taken it outside, log of 3.8 into 10 to the power of minus 3. This will be looks like log A into B. What is the formula? Log of A into B is nothing but a log A plus log B. This is a formula which we used. Correct now? So, minus log of A is 3.8 plus log B is log of 10 to the power of minus 3. And we know that we have one more formula, log of A to the power of B, which is nothing but a B log A. Now, we can write this above equation as minus log 3.8 plus minus 3 into log 10. We know that log 10 value will be equal to 1. So, what is the log of 3.8? The log of 3.8 that you need to see under 38 under 0. So, 38 under 0 log value is 0.5798. 0.5798 is a log value. And since we have only the two numbers and we have a point between the two number and we have to use a 0 for that, as we have already learnt in our previous class. So, it is minus 0.5798 0.98 minus 3. So minus into minus, it will become plus, and I can rewrite this as 3 minus 0.5798. So if you subtract 3 with the 0.5798, you will get 2.42. So which is nothing but a pH. So what is the value we got? 2.42 is a pH of the above solution. Hope you all understood with this numerical. We'll go with the next one. Calculate the pH of 0.02 molar of barium hydroxide solution by assuming complete ionization. Barium hydroxide which undergo ionization processes to give B2 plus 2OH minus ion. Correct, no? This is the equation. They have given the molarity of barium hydroxide, that is 0.02 molar. We need to calculate the pOH of the hydroxyl ion. So it is 2 into 0.02 and it is nothing but a 0.04, or you can write this as 4 into 10 to the power of minus 2 molar just by shifting the decimal. Now, we have the hydroxyl ion concentration, but we need to calculate for pH. So first I will take out the formula to calculate pOH. pOH which is equal to negative logarithm of base 10 to the hydroxyl ion concentration. So negative, I will take it outside, log of 4 into 10 to the power of minus 2. So, hope you know that if the log A into B is there, we need to apply a log of A plus B. So, minus log 4 plus log of 10 to the power of minus 2. So, I can rewrite this above equation also as log 4 plus minus 2 into log of 10. Log 4 in the sense you need to find out the log values of 40, okay, under 0. So, what is the value of log 40 under 0? It is 0.6021 minus 2, okay, log 10 value it is again 1. Now, I will take 2 minus 0.6021, and if you solve 2 minus 6021, you will get 1.3949. So, this is what? pOH. So, now we got the values for pOH, that is 1.3949. But in the question they have asked to calculate the pH, correct, no? How we can calculate the pH? We have a relationship, that is pH plus pOH which is equal to 14, correct, no? So, we need to calculate what? pH. I will take it outside. So, it is 14 minus pOH. So, 14 minus, what is the pOH value we got? It is 1.3949. So, if you subtract 14 with the 1.3949, you will get 12.6021. You will get what? 12.6021, which is a pH of the solution. Like this, you know, first you need to calculate for the hydroxyl ion concentration. If they ask you to calculate the pH, you need to take up that relationship between the pH and pOH. Then you need to solve the problem. So, hope you all understood with this small numerical. Next, we have calculate the pH of 1.0 into 10 to the power of 8 molar solution of hydrochloric acid. In this numerical, if you directly put the pH which is equal to negative logarithm of H plus ion, you will get the pH value which is more than 7. So, that equation if you put, it's not suitable for an acid, because already we have understood that the pH of an acid, it will ranges from 0 to 7. So it should come below the 7 only. So that we have to take the concentration of water also. So we have a relationship, molar concentration of the H plus ion into molar concentration of the hydroxyl ion, which is equal to what? Ionic product of water, and it is equal to 10 to the power of 14, which is equal to how much? 10 to the power of minus 14. Now, I'll take out only the molar concentration of the H plus ion, which is equal to 10 to the power of minus 7, or which is also equal to the hydroxyl ion concentration. So, now I'll write the H plus ion concentration from the water is 10 to the power of minus 7, and H plus ion concentration from the acid is 1.0 into 10 to the power of minus 8. Now, in order to get the H plus ion concentration, I'll add these two value. You will get 1.0 into 10 to the power of minus 8 plus 10 to the power of minus 7. If you see this, you can see that 10 to the power of minus 7 is common. So, I'll take out the 10 to the power of minus 7 as common. Remaining is 1.0 into 10 to the power of minus 1 plus 1. So, nothing is there. Now, 1.0 into 10 to the power of minus 1 in the sense 1 into 10, which is equal to 0.1 plus 1 into 10 to the power of minus 7. And you can rewrite the 0.1 plus 1 as 1.1 into 10 to the power of minus 7. This is actually the hydrogen ion concentration. That is a H plus ion concentration. Now, by using this H plus ion concentration, we can easily calculate the pH. That is pH, which is equal to negative log of H plus ion. So, negative log of, what is the H plus ion? We got 1.1 into 10 to the power of minus 7. So, it's log A into B again, log A plus log B. But our log B will be looks like log of A to the power of B. So, I will rewrite this as log of 1.1 plus minus 7 into log of 10. Log of 10 is 1, and log of 1.1 in the sense you need to see the log of 11 under 0, because no other digits will be there. You need to see the log of 11, and the log of 11 value is 0.044, and remaining is plus into minus 7. Log 10 value is 1. Now, plus into minus, again it will become plus. So, I can write the 7 minus 0.0444, and you will get, if you subtract the 7 with the 0.0444, you will get 6.958. This is actually the pH of the solution. Okay. This is how you need to calculate the pH of the solution. But if you see that virgin values of hydrogen ion concentration, it is too high and it comes above the pH of an acid. That is why I have considered this method to calculate the pH of the acid, and you can see that the value is below 7. Hence, the solution is strong acid. Okay. Next, the pKa of acetic acid and pKb of the ammonium hydroxide are 4.76 and 4.75 respectively. Calculate the pH of ammonium acetate solution. We have a relationship with the pKa and pKb with the pH. That is, pH is equal to 7 plus half into pKa minus pKb. Correct, no? So, it is 7 plus half into, what is the pKa value they have given? It is 4.6 and 4.75. So 4.76 minus 4.75. If you do this, 7 plus 1 by 2 into 0.01. So if you divide 0.01 by 2, you will get 0.05, and if you add to the 7, it becomes 7.005. This is a pH of the solution. Okay, it's very easy and you can put it with this relationship to obtain the pH of the solution. Next we have, calculate the pH of 0.1 molar acetic acid and dissociation constant of acetic acid is 1.8 into 10 to the power of minus 5. So here they have given the acetic acid, that is CH3COOH, which undergo partial dissociation to give acetate ion plus H plus ion. But they have given the dissociation constant value, that is Ka value they have given, it is 1.8 into 10 to the power of minus 5, correct now? Now if you see that this is the acetate ion and they have acetic acid which is dissociated to give acetate ion as well as with the H plus ion, and they have given the dissociation constant value. Now we have a relationship to calculate the molar concentration of the H plus ion is a square root of Ka into C. So what is C here? They have given, that is 0.1 molar. So that square root of Ka is 1.8 into 10 to the power of minus 5 into 0.1. If you do the multiplication then with the square root of this number, you will get 1.341 into 10 to the power of minus 3 molar. This is a hydrogen ion concentration. After obtaining the hydrogen ion concentration, we need to calculate the pH of the solution. What is the formula we have? pH, which is equal to negative log of H plus ion concentration. So negative log of, I'll take the negative outside, 1.341 into 10 to the power of minus 3 it is. So it looks like a log of A into B. So log of A into B is nothing but a log of A plus log of B. Correct now? Now log of A I'll write as such. Log of B looks like log of A to the power of B. So it is minus 3 into log 10. So log of 1.341, if you see, okay, you have to see under log of 13 under 4 and you need to add the mean 1 for that. Okay, so mean value under 1, what you will get? You need to add with that number and you will get the log value as 0.1587 minus 3. Okay, this is a log value of log 1341. Okay, now if you multiply with this number, you will get 3 minus 0.1587. So if you subtract the 3 with the 0.1587, you will get the answer as 2.8413. This is a pH of the solution. Okay, this is a pH of the solution and you need to solve with this formula to calculate with the H plus ion concentration, then move towards with the pH formula, then calculate the pH of the solution. So hope you all understood with the numerical. So in the next class, we are going to discuss with the last topic of this unit, that is a common ion effect. So hope you all understood with this unit. I'll come back with the last concepts of this unit. Till that, take care and be safe. Thank you.